What we're going to be taking a look at here in 3.1 is solving systems of linear equations specifically by graphing. We only have one objective, solve systems of linear equations by graphing. So let's dive into it and see what we can remember first off about just simple basic equations. So before we get to a system, let's just talk about a single linear equation. Remember that the solutions to a single single equation is simply all the points that satisfy that line. So that orange line there, let's say that's our equation. Any ordered pair on that orange line would be considered a solution. Be like if we're doing a t-chart, any ordered pair that satisfies the equation, that would fall on the line. It doesn't mean that it's every ordered pair, because look, I can put some dots out here in sort of space, and obviously literally space, no pun intended, but notice these dots here, they do not fall on that line. So therefore these are not solutions to that equation right here. And so even though there may be an infinite number of dots on that line, it's not every dot. Okay? It's just the dots that fall on that line. So here's an example of one where you can see the ordered pairs 1, 0, 2, 2, 3, 4, and 4, 6 all been plotted for you over here. And when we connect those dots, now how do we know to connect dots? It's an equation. If you remember that from chapter 2, anytime you have an equation, you want to connect dots. These are simply a sampling, giving us a sample of what the entire equation would look like. So there's still all these other dots that we haven't listed. We don't really need to if all we're doing is trying to graph. Okay, but all of them would be considered solutions to that. So what really, to summarize what we just talked about here, is that there's an infinite number of solutions on some type of equation. And so here specifically talking linear, there's an infinite number of dots on that line. Now when we talk systems of linear equations, what we're talking about are two or more equations that are put together to form a system of linear equations. So in other words, instead of just having one line on a graph, so something like this, instead of just having one, we may have a second one. And so we have two lines on one graph. So that's called a system, is that graphically is where you have two or more linear equations that we have on a single graph. Now, the definition for the solution to a system of linear equations, and notice this is starred, so make sure to get this in your notes, is any ordered pair that makes both equations within the system true. The point where the lines cross is the solution to the particular system of linear equations. Now, let's talk about this for a minute. What we're talking about is we're talking about the intersection point. When you have two or more graphs, linear equations, I should say, there's one of them in white, and we'll put the other one in sort of this pink color. And what we're looking for is, do they share a single point or points? So the intersection could be a single point, or it could be a points that we're looking for. An ordered pair, okay? An x and a y. There's our x, there's our y. So notice that one single point. All these other points that fall on each line, like that point satisfies the white one, but doesn't satisfy the pink one. This dot satisfies the pink one, but not the white one. We're looking specifically for the dot that satisfies both at the same time. That's called a system of equations. There's really three different types of solutions that you're going to get. You can either get one solution, that's the one we just sort of looked at. We'll look at it in just a moment. What you have is where they intersect at one spot. That's traditionally your main one. You can have zero solutions. We'll look at that one in just a moment as well. When do we get no solutions, in other words? And then there's times where you get an infinite number of solutions, and that will be an interesting one to talk about, is how do we write our solutions? Because your Algebra 2 book, and we're going to do some college algebra there as well, to sort of, when we write our answers for infinite number of solutions. But first, let's take a look at the single one solution where it crosses at one single point. So what we do is we have a linear equation right here in green, we have a linear equation in red, and what we're looking for is there a value where they cross. Now, what we'll do here with us, because we don't have graphing calculators necessarily to utilize for this, is that all of our graphs are going to end up crossing at a really nice spot. If it doesn't cross exactly, let's say this is just slightly up here, because we have human error and we may graph and it crosses up here, then we want to check some ordered pairs around. All your answers are going to be integers. So keep that in mind, is that your solutions will be integers. I won't give you anything that are fractions or decimals or anything like that, unless we use graphing calculators, and then we can find that. So in this one right here, if I want to know what is that ordered pair where they intersect, well, what's my x value? 1, 2, so my x value is 2, and then there's 1 hidden right there, and that looks like it's probably 1 right there. And if you're not sure if it's 1 or 2 for the y, try 2 comma 1 into your equations, and it has to satisfy both equations for it to be a solution. In this case, we don't have solution or equations up here, so 2, 1 is our solution for this one. So there's one solution. Here's an example of no solutions, and it's when we have parallel lines, because parallel lines never intersect. And so if we're looking for intersection points, and there are none, how can there be a solution? And so this is an example where if they're parallel, how do we know? So we know that if we get parallel lines, the answer is no solutions. But how do we know 2 equations are parallel? Because 2 lines could look like they're parallel, but may not be. How do I know for sure? Well, if we go back to what we did back in chapter 2, and we talk a little bit about slopes, don't parallel lines have the same slope? So if you have 2 equations that have the same slope, but they have different y-intercepts, then we're talking about parallel lines. And so if you put them in slope-intercept form, here's a real quick example, 3x plus 4 and y equals 3x minus 2. Notice they have the same slope, okay, but they have different y-intercepts. They're parallel. They're parallel. Therefore, there would be no solution to that system of equations. There's no intersection. The last one would be when there's identical lines, when the 2 equations are exactly the same. They have an infinite number of solutions. All these green dots here, and I could keep adding more, all represent where they intersect. They intersect all the time. I could keep going. This would be wasting our time if I kept going. But there's an infinite number. Now, it's not all reals. Don't fall in that trap. Not all reals. Because this dot right here isn't a solution. So there's an infinite number of solutions, but it's not every ordered pair. We've got to be careful of that. It has to be a very specific type of ordered pair. And so we'll talk about how to write those. Your textbook will end up writing the equation. Whatever the equation is, whatever satisfies the equation is your solution. So what you'll see in your textbook and what you could use is just the equation of the line as your solution. Now, when I write the equation of the line, you don't write the equation of the line, literally. You want to write whatever the equation is. So like the example, y equals 3x plus 4, let's say that was the equation twice. That is your solution, not the words equation of the line as your solution. So again, when we practice those, hopefully you'll get accustomed to that. Okay? Let's take a look at one that's already been graphed for us and just make sure that we identify where the solution is. So where do we look to find the solution? Where we look at the intersection point. So what we find is that it intersects, it looks like right there. So it looks like 1, 2, 3, negative 3, okay? And then 1, 2. So it looks like to me it'd be negative 3 and positive 2. Again, if you're not sure, because we do have some human error when we graph these things, we want to be as accurate as we can, but if we get slightly off, just make sure it works back into the system. So we don't have any equations to try it in on this one, but if we did, that's where we would try it. If we take a look at now, we do have some equations. Now let's go ahead and graph them and find the solution. So notice both of these, and I'm going to do the one in purple and purple. I'll do the one in green and green so you can see the difference. So let's do the purple one. Y equals 2x plus 1. I need to graph that. Well, how do I graph equations? Well, there's 2 ways. You can either use a t-chart, or you can put it in slope-intercept form. Well, I know which one I'm going to use, and I bet you I know which one you're going to use on this one as well, and that is the slope-intercept form, because it's already in slope-intercept form. And so we can go ahead and we go, well, the y-intercept is 1, and our slope is up 2 over 1, or down 2 over 1. And what you find is it's an equation, so we connect the dots, and there's our first line. Now if we go ahead and do the one in green, and it's in slope-intercept as well, notice it crosses at 1. Wow, that's pretty awesome. And then 1, 2, 3, and over 1. It's a negative slope, so we go up 3 or down 3. 1, 2, 3, and then over 1 this way. So whichever way you want to do it. Get the same equation. There's our same line. And then if we want to go ahead and state what the solution is for this, notice where they intersect. Right there. What is that point? Remember, the point is the solution. So the solution here, what's our x value? Looks like it's 0. What's our y value? 1. Now, how do I know that's the solution? Let's come back over here and plug in 0 and plug in 1. You get 1 equals 2 times 0 plus 1. Is that true? Sure it is. Is 1 equal to negative 3 times 0 plus 1? Also true. Sure it is. It satisfies both. My solution is 0 1. X is 0, y is 1. You can either leave your answer in order pair, or if you wrote it like this, that's okay as well. But you need to make sure to label which one is x and which one is y. Okay, let's take another look at another example here. Graphing this system of linear equations. Notice, again, both of these are in slope-intercept form, so we will go ahead and use the slope-intercept form to help us graph. But before we get going, notice here, I'll mark this and see if any of you can recognize this. Do you see how, since they're both in slope-intercept form, they have y equals mx plus b. Y equals mx plus b. Notice the slopes are the same, and notice that they have different y-intercepts. Now, if they have the same slope and different y-intercepts, what that sort of hints towards is that these are going to be parallel. Now, that's something that you can sort of just wrap your brain around and grab onto and then just remember. Or simply, let's just graph these two and see what it looks like. So again, the purple one I'll do in purple. And what we have here is we have a y-intercept of -1. That's our b. And then we have a slope of 2, up 2 over 1. Because remember, 2 is the fraction 2 over 1, rise over run. So there's we got there, and I'll put another point just to help me out. And there we go. There's our line. Now let's do the green one real quick. And again, what we have is we have a y-intercept of +2. So there we go. We also have a slope of 2. So the slope is 2. The y-intercept is 2. Okay. This 2 is 2 over 1. And so what we have is up 2 over 1. Or down 2 over 1. And what you'll notice is, even with me graphing it freehand, you can notice that those lines, for the most part, are not going to intersect. What definitely gives it away is if they have the same slope and different y-intercepts. They're parallel. Parallel lines never intersect, and therefore, what your answer should be on one like this is no solution. So if they're parallel, you would have no solution. They don't intersect anywhere. The next one we'll take a look at here is now they're written in more standard form. So we have to do a little bit of work before we get to the graphing. So again, if I'm going to use slope-intercept, which is what I would do, I'm going to go ahead and get my y by itself. This is what I want to isolate. So I'm going to subtract x from both sides. So I end up getting y equals -x minus 2. Now it's in slope-intercept form. I got -2, and I got a -1 slope. So down 1 over 1, or up 1 over 1. Remember, it's negative, so it should be downhill. And so we'll look something like that. And so I'll go ahead and try to graph this best I can. And there we go. So there's the purple one. Now if we take a look at the green one here, again, I got to put it in slope-intercept form. So I'm going to end up adding 2x. Let's move that to this side. Man, my 2's look bad. And then you got, don't forget your negative still in front of the y. Sometimes we forget that. That's something we definitely don't want to forget, because now to get y by itself, I've got to change. I got to multiply everything by a -1, or change the sign of everything. So the negative y becomes y, -2x, then -3. And so what we have here is we have our slope-intercept form. Now notice the difference here. These are definitely going to intersect somewhere, so that's good because they don't have the same slope and they don't have, they're not the same line at all. And so we go ahead and we go to -3, 1, 2, 3. And then our slope is -2, so I go up 2 over 1, up 2 over 1, or down 2 over 1. There's our -2 slope. Draw a line, and now what we're looking for is where do they intersect? Well, it looks like to me they intersect right there. So what is that point if we had to label it? It looks like -1, -1. Okay, well, let's make sure that's the right answer. So what we'll do is come back and plug it in. I just plug it in right here. What's -1 plus a -1? Does that equal -2? Sure it does. So it checks off this one. It has to work on this one as well. So -2 times -1 minus a -1 equals 3. So I just simply substitute in for y and for x. Okay? And so I get 2 plus 1 equals 3. Absolutely it does. And so my answers are -1, -1, or x equals -1, y equals -1. That's where we're at there. Okay? Taking a look at this next one is really going to be the last one we take a look at here. And if you notice on the first one, it's in slope-intercept form. So I'm going to go ahead and graph it pretty quickly. Then we'll look at the second one. We have to manipulate it a little bit. So our y-intercept is 2 and our slope is 1/3. So you can go up 1, 1, 2, 3, and over 3. Or you can go down 1 this way and then 1, 2, 3 that way. Okay, so we get a few points. So it looks like something like that. Okay, so there's our equation for the first one. Now the second one is not in slope-intercept form, so let's go ahead and rearrange it by adding x to both sides. So I simply added x to both sides. Then I divide by 3. Now remember what's in front of x is a 1, so when I divide it by 3, I actually get 1/3. And I divide 6 by 3, I get 2. And so what I have here is 1/3 x plus 2. Wait a minute, that looks awfully familiar. Yeah, it should. You see how they're exact same equation? So when I graph the green one, it's going to be exactly right on top of the purple one. So what we have is the exact same equation twice. Didn't look like it when we started, but it was. So we have an infinite number of solutions, but that doesn't tell me what the solution is. Okay, now your book, your textbook's going to have you just write the equation, which is perfectly fine. Okay, it's 1/3 x plus 2. It doesn't matter which equation you choose. They're both the same, even though they look different. So that's actually the equation. But on the next slide, let's describe how we can write our solutions another way. A little bit more like the way that we would do in college algebra. So if we look at a problem like this, let's go ahead and walk through solving it again. If we go ahead and graph this thing, I'm going to go ahead and throw up a graph here real quick. Actually, I'll just draw it. And so we'll just do this, and if we go ahead and plot some points here, or put it in slope-intercept form, this is what we get. So 1, 2, put a dot, and then we have a -1 slope. And so we get something that looks like this. Okay, so we're in pretty good shape there. This one right here, I'm going to go ahead and add 3y, just to move it. I like my y's being positive, so I'm going to move that over there. And then I'm going to subtract 3x to put it in slope-intercept form and divide everything by 3. To get my y by itself. STD, stack and simplify. So I stacked it, I get -1, 6 over 3 is 2. Now look at these two, they're exactly the same. So if I graph it again, it'll just be the same y. So we knew that we could just simply circle the equation, that's it. The college algebra, what we learned is this. We want to put it as ordered pairs. So everything we've been doing has been ordered pairs, but now, for whatever reason, we switch over and we write the equation. However, I can write this equation either in terms of x or in terms of y. So let's do terms of x first, because it's actually already done for us. X can be whatever. So let's say x is 3. If x is 3 and I plugged it in, I would get -1. So if x was 3, I should get -1. How do I represent -1 not using -1? Because x can be anything. Well, what I want to do is I want to solve for y. So this is the y, right? So I want to solve for y in terms of x. So in other words, here's y in terms of x. X is what it's in terms of. So I can come back up here, and whatever y was, I could put it in what they call in terms of x. So now if you give me any number, 0, let's say x was 0, we should get 2, right? Okay, so if I plug in 0, I get 0. And what's -0 plus 2? Opposite of 0, 0 plus 2 is 2. I get 0, 2. There's more repair. Well, we should get 1, 1. Okay, let's see if we get 1, 1 here. If I plug in 1, then if I plug in 1, I get 1. There we go. So every x that you choose will satisfy that line written like we have it right there. And I really like that. It's really a neat way of writing your solution. It's a little bit more complicated, but definitely is a neat way of doing it. Let's finish this off with in terms of y. Now this one's a little bit harder because we don't have anything in terms of y. Everything's been in terms of x. Very easy to do this. All you've got to do is get x by itself. Okay, so let's go back up and use x plus y. I'm going to write it over here so we can see. X plus y equals 2. Solve for x. Okay, so you end up getting 2 minus y. Subtract y from both sides. See, now I have x in terms of y. And so I can come over here, and that would be my solution in terms of y. It really doesn't matter. Most of us will probably do this because we're going to go to slope-intercept form. That would be great. If you can do this, that gets you that much closer to your level for college algebra, and that's what I want you to do from Algebra 2, is take that next step up, and this is one way of doing that. This is section 3.1, graphing systems and solving those through this idea of graphing.